Okay, so now the next thing I want to do is I want to be able to turn on the various LEDs that are on this board. Okay, so the first thing you want to do is figure out where these LEDs are connected and what they are connected to. Only then I'm going to be able to uh, drive them. So I go here, and the first thing that I need to look at is this little PDF that contains the schematic. Okay, so this is the first page, second page, third page, and so on and so forth. So one thing to note here is that the schematic is quite large. So what you see here is that the IC itself. So this EM4C123G. Okay, this is actually this controller here. So this is called U1. U refers to IC, and U1 means this is the first IC that we are talking about. So U1, and it's not possible to draw or annotate all the pins in one diagram, so they split it. So this is U1A that contains uh, some or most of these things. And then if you search for U1 again, you will find that U1 may be appearing in other places as well. So you can see this is U1B. Okay, so parts of the IC, some pins, for example, on the ground pins, the power pin, the crystal oscillator, reset pin, wake up pin, all of these things, they just split it into a different blocks. That's all. So all it means is that U1A and U1B, they both refer to this particular chip, and this is the one that we are uh, working with, and we are going to program and dump our code into this and so on and so forth. Now it turns out that this board also has another microcontroller up here. Okay, and that happens to be U2. Okay, and you'll see that U2 is connected to this particular interface. You can see this is our USB micro, and this is called J11. If you notice, there should be an annotation somewhere that shows that this is indeed J11. Maybe it's on the underside. Uh, but anyway, you can see that this is U2. It's clearly marked as U2. Okay, so this chip up here, you can see that up here it says U2. So this is the chip that is basically talking over USB and acting as your interface between the computer and this particular chip. And this is the chip that is actually being used for whatever we are talking about. So this you can see is U1, and this is the designator U1 that is, so this is U1. So I need to figure out where the LED is connected to this chip. So let's go and see where these LEDs are connected. So fortunately, they are right here on page 1, and you can see that there are 3 LEDs. There is R LED, green LED, and blue LED. Those 3 LEDs are here, and these 3 LEDs are connected to these 3 transistors, and they are connected to 3 signals: LED R, LED G, and LED B. Okay, so where does LED R come from? Let's see. So just hovering over that very nicely, it gives me on page 1. Let me just click on this. There we go. So LED R, LED B, and LED G. Okay, they come from these 3 resistors, and where are they connected? They are connected to our port F. Okay, so PF0, PF1, PF2, PF3, PF4 are up here. Out of this, PF1 is connected to LED R, PF2 is connected to LED B, and PF3 is connected to LED G. So red, blue, and green. So in very simple terms, if I have to let's just quickly draw it. So this is my sorry. Let's do options. 10 options. You don't want to. So this is what my port F looks like. Okay. Okay. And this has, of course, there are 8 signals on this. Okay. So this is port F0, port F1, port F2, port F3, port F4, port F5, PS0, PF1, PF2. These are the 8 pins on this signal. Okay, so not all of them are shown here. 0 to 4 are shown here, and then let's see that PF. There is PF6. So you can see PF. So this board doesn't even have the higher bits for port F available to for general use. That's my guess. Maybe maybe they're reserved or they're used for something else. That is possibly the case. So nevertheless, we know that we should be concerned only with the lower 5 bits, which is 0, 1, 2, 3, 4. Okay, so now let's see. This particular one is connected to a switch. Okay, next one is connected to red LED. Okay, port F1 is connected to this red LED over here. Then next one is connected to PF2 is connected to blue LED. Okay, so that is blue, and then the next one is connected to green, and then finally this one is connected to another switch. So now basics of color combination. Let's say you want white, you would want all of these three to be on. So you want to output 1, 1, 1 on these three pins. Of course, these switches you don't really care about, so everything else will be 0. So if this is the case, then hex E. This is going to be the binary pattern or the bit pattern that is going to generate white LED, white color. So green, blue, and red all are on. Okay. If you want only, let's say, if you want only red, you want this to be off, this to be off, which means your pattern should be hex 2. Okay. If you want only blue, you want this to be on, you want this to be off, you want this to be off. So what is your pattern? Your pattern is hex 4, and so on and so forth. Okay. So now that we have that clarified, let's go and try to figure out how do I turn these port pins on. Okay. So to do that, first thing you have to do is go and look at this data sheet. And why data sheet? Because GPIOs are implemented not by the ARM core and not by the architecture, but by the implementation. Whoever has implemented this particular microcontroller. So let's go on and search for GPIO. So right here in the index, basically, or the contents section, table of contents, you will see all the subsystems. Okay, so first architecture, then about the processor itself, then the Cortex M4 peripherals, which means things that are part of the core. You can see SysTick timer, the NVIC, control block, memory protection. All these things are part of this sort of core. They're really closely tied to the core. Then you have a JTAG. Then you have your system control, that is your power control, all those things. Then exceptions, hibernation we are not looking into right now. Then of course that internal memory and all that we talked about. DMA will skip for the moment. We'll come directly to GPIO. Okay, so within GPIO, so now we have 6 physical blocks of GPIO, and each is sort of organized into, all these pins are mapped into or organized into ports. We call them port A, B, C, D, E. Okay. The one we are interested in is called port F. Okay. So what all do we need to do? What all do we need to do to be able to access these ports? So let's take a look. The signal description. All these GPIOs have alternate hardware functions. They either function as general purpose GPIOs, or they function as something else. So let's see what those alternative functions are and whether we want to enable or disable them. So normally, for example, on port A we have UART. On this again on port A we have SSI, we have I2C, we have JTAG on port C, and then remaining things are all uh, basically all shown here. Okay. So normally, and of course these details are given here. So which pin and what is the analog function, what is the digital function, and so on and so forth. It's all very nicely given here. So we are concerned with PF0 and PF1. Okay. So PF1 can potentially have any of these functions, which means timers, PWM, CAN, SSI, UART, and so on and so forth. Okay. So we are not really concerned with any of these. We want to make it work as a general purpose IO pin. So let's see what that entails. So every pin, which means PF1, PF2, whatever it is, that is basically this particular pin. It is controlled by all of these signals. Okay. So what all do we have to enable? First of all, we have to make sure this output is enabled. Okay. So to do that, we have to make sure that the GPIO output is enabled. Okay. So who enables this output enable? That is enabled by this data control block. So GPIO data and GPIO date are something that we need to write to. So let's make a quick note of these things. So let's put a comment here and say what is it that we need to write to or enable. So GPIO data and GPIO date or direction. So GPIO data and GPIO date. These are two registers that we have to look into. Okay. Then what we have to look at this one. So this is coming from this alternate output enable. Okay. So this is GPIO P CTL, which is something that we may need to write. So let's see whether we have to disable it or the GPIO P CTL. Let's PCL. So we'll go and see what that is. Then alternate inputs are not being used anyway, so these are no use to us. We don't care about these bits. These alternate outputs again not being used. We are not using any of these alternate outputs, so we don't care about enabling those peripherals. And then we also have that's pretty much it. That's all we care about. Okay. So then we have to look at the pad control. Okay. So let's look at all of these registers. So let's copy this and we'll go see what each of these registers are intended for. Okay. So we'll go to the data sheet and check. Then these analog things we are not using anyway. Okay. So there we go. GPIO DIR. Okay. So the first thing is GPIO direction is used to configure each pin as an input or as an output. Okay. So GPIO dir configures each pin as input or output. Okay. So we'll figure out what value we need to put here. Let's go take a look. So for GPIO dir, you can see that it's a 32-bit register, and all these bits other than the lowest 8 bits are basically reserved, which means you shouldn't read to them, you shouldn't write to them. Okay, so software should not rely on these, and you shouldn't write to them. You should definitely not write to them because it's RO, it's read only. So don't write anything to them, and we only care about these lowest 8 bits. So what do we need to do? Whichever pin we need as an output, the corresponding bit should be 1. Okay, so for port F, what do we see? That the lowest 5 pins were of use to us, and out of that, you can see that this pin needs to be an output, this pin needs to be an output, this pin needs to be an output. All of these need to be just inputs. Okay, so what is the value that we need to write? This value turns out to be hex key. Okay, so this is going to be the value that we need to write. Okay, and that is hex key. So we are done with GPIO DIR. Let's look at the Let's look at the subsequent registers. What is GPIO data? GPIO data actually is the data register. Values written to GPIO data are transferred onto the GPIO port page, which means that if you write something here, that is the data that appears on the port page. So if you want white light, you need hex key to be put in the data register. Then let's go back and see what are the remaining registers. Where will we? we were we were here. Okay, so we looked at direction already. GPIO data, GPIO data register using this. You don't have to worry about which register and all those things. Okay. So so this is an interesting way to uh, uh, do read, modify, write, which we will come to later. Okay, so don't get hung up on this for now. But basically, we need to write values into the GPIO data to get them to be on the output pin. Then interrupt control, we are not using interrupt controller right now, so ignore that. ADC trigger, not using that. DMA, not using that. Mode control, yeah, mode control is needed. Mm, further pin muxing, yeah, none of this is being used right now. Okay. Then let's come to commit control. So GPIO commit control register provides some protection against accidentally programming of critical hardware. Okay, so let's say you have something critical connected to these things, some way to protect from having arbitrary code just writing random values to it. Okay, so let's see. So let's go and take a look at this. So writes to the protected bits of GPIO alternate function select. Okay, so let's go and look at this register. Then pull up select, pull down select, and digital enable are not committed unless GPIO lock register has been unlocked and the appropriate bits have been set. Okay, so let's go and look at this particular one. So GPIO lock register enables writing access to this control register. Okay, so you have to unlock all of these registers by writing a specific value to this particular register. Now it turns out that these two registers, GPIO commit and all, they are only controlling specific pins. They are not controlling all the pins. Okay? Now we need to figure out which pins are actually being controlled by this commit register. For that, we go up here, and just to be honest, it's not very well written in this particular data sheet, but we have to go digging a little bit to find out where it is given. So there you go. So you can see this PD7 and PF0. Okay, these are the only pins where they are considered as GPIO by default, but is locked and can only be reprogrammed by unlocking the pin in this one. Okay, so it's only PF0 and PD7 that really are controlled by this GPIO lock and commit control register. For the remaining pins, which is the LEDs that we are talking about, you don't have to worry about these at all. Okay. So then, what is the next register we need to worry about? Let's go to our code again. That was our, so this one. Let's do this one by one. So this one was pull up enable. This one is pull down enable. Pull up register and pull down register. Okay. This one is our GPIO digital enable, which you need to make. Basically, you need to make the whole thing as a digital port. Okay. What is this AMSC? Let's go take a look at AMSC. This is analog mode select. Okay. So on page 687, this is only for valid valid for ports and things that can use as ADC input. Okay. So what do we need to do for this? We need to write a 1 to the corresponding pin to enable analog mode. So obviously we are not going to use this at all, and anyway it boots up with value 0, so we can ignore this. Okay, so this is analog mode enabled, and should be written to 0 or need not be, nothing need be done here. So let me just get rid of this. We don't need this. So DEN definitely you need to enable this, and what is the value you need to write? You need to write a 1 to the lowest 5 bits. Okay, we need to write a 1 to the lowest 5 bits because we want all of these 5 to be digital outputs. Sorry, to be digital pins, not analog pins, but digital pins. And so we are going to write a value that is 5 ones in the lowest place. And so this value turns out to be hex 1f. Okay. Then what is this GPIO-DR? Let's go take a look at that also. So what is GPIO-DR? This is open drain select. Again, we are not going to use GPIO-DR. So let's go and see where is our register description. There we go. GPIO-DR. We are not going to do anything because none of these we wanted to be open drain. We want them to be digital pins. Then what is the next one we want? What is this SLR? Let's go see what is SLR. So maybe put a bookmark. So SLR, there we go. Slew rate control select. So again, we don't really care that much about slew rate. So normally slew rate control is enabled or disabled. We don't care. We are driving basically a fairly slow LED device, so I don't care about this. But let's just put this. Okay. This one, DR8R. Okay. This is drive strength. So let's go find it again. DR8R. The next is somewhere. DR8R. So this is the 8 milliamp drive control register. So whether or not we want 8 milliamps of drive strength, so this is whether it is 8 milliamps drive or not. So this is basically, we don't care about this. We don't want high drive strength because anyway there's a transistor on the output. So we want to set this at 0 or we're not going to enable this at all. Okay, similarly, if you look at this 4 mA drive strength, this is also by default 0. So that means we are not even driving 4 milliamps. What about 2 milliamps? It's not set to. It is 0. So either it is controlled by DR4R or it is DR8R. We are not set. Okay. So what is the drive strength by default? By default, all GPIO pins have drive strength 1. You can see that on reset, they all sorry, they all boot up with SS, which means all pins are set to 2 milliamps drive strength. So that's okay. That's more than enough for us. So all of these three registers, we don't care. We are going to just go with whatever default drive strength is available to us. Next, what is the next register we need to write to? That happens to be this GPIO PCTL. So let's go and see what this PCTL does. So data direction we have already seen. Interrupts we are not using. Where is PCTL, port control. So let's go. So this port control is used in conjunction with AF select. Okay, the analog function select selects which peripheral is used for each of these things. Okay, so we are anyway not using uh, any of these peripherals, which means we are not using any of these special functions, and therefore there is really no reason why we need this PCTL to be uh, on. Okay, so you will see that for PCTL, if it has to be on, you know, 1, 2, 3, whatever is enabled. These are all for these special functions. We are not using any of them, and therefore we don't need any of these. Okay, so in general, what you should do is you should go here and up here, whenever we are using the GPIO module, right? So the first thing that you should do when you start using the GPIO module is look at this entire register map and go to each register and just get some idea about what each of these registers is going to do. Because if there is some functionality, it has to be controlled by some register. And if there's no register to do it, then basically it doesn't have that functionality. Okay. So data is basically the data that you want to write. Direction is uh, whether you want it to be input or output. Interrupt sense, whether we are going to detect interrupts, whether we are going to detect one kind of edge or both edges. Interrupt event, we don't care. Interrupt mask, we don't care. Raw interrupt status, we don't care right now. All of these are interrupts. Okay, so we don't care about this. Alternate functions we are not using because we are not using any alternate functions. We know that this GPIO 2 milliamp drive is default. You see it boots up with this in FF mode. So 2 milliamp drive is good enough for us. That's fine. We are not going to enable this 4 milliamp or 8 milliamp drive. We don't want open grain. We don't want pull-ups. We don't want pull-downs. Then slew rate, again, we just go with the default. We don't want to control slew rate at all. Digital enable, definitely we want to enable digital enable. So you can see that is this DEN. So you need to write to DEN. Lock commit, like I said, we don't need to write because none of the pins that we are using are protected, so we can ignore that. Analog mode select, we are not using any analog mode. GPIO port control, this is for the analog functions which we saw, don't need it. ADC control, not using it. DMA control, we are not using it. And this peripheral identification, let's just take a look, but we are not using it right now, so let's, yeah, there we go. So, each register contains 8 bits of the 32-bit registers used by software to identify the peripheral. So again, we are not using this for now, so we just ignore this for the time being. So let's just write some very, very simple code that is able to write these values into these registers. Now, how do I write value into this register? Okay, so I need to know what is the address of this particular register so that I'm able to write to it. Okay, now one way is, of course, we can go here, for example, GPIO data. Okay, and I can search for GPIO data. And we will get its address. There we go. GPIO data. Offset is 0, which means, you know, GPIO port F. Okay, so depending on whether you are using APB or AHB, the base address is this. So this is the address that we have to write to. Okay, offset 0 meaning base address is this, offset is 0, so this is the this is the address of this register. But this is quite clunky, and remembering all these and then hard coding them, it's quite difficult. So fortunately, we have with us one header file that has been given to you. Okay, so what I'm going to do is I'm going to copy that into this particular project. So what I'm going to do is I'm going to say new. I'm going to say header file, and this header file is going to be called basically the part number that we are going to use. Dot h. Okay, source folder is the same. Default C header template, and then finish. Okay, so this is our uh, this is the header template. Now, what should be the content inside this? This also has been given to you in one of the older files. So you just control paste this whole thing, and we are done. Now, what does this file do? This file basically tells us, this is basically a bunch of hash defines that tells us what are the addresses of all of these registers. Okay, so we just saw that this GPIO data register, right? So it has an address with an offset 0, and this is the base address, right? So we have just seen this. Let's go and see for port F, by the way. So we are interested in this port F. So let's go and see for port F, GPI registers for port F. Let's go and see where is our data register. So you can see that this data register is defined as having an address 4002 5 Okay. So basically now if I want to write to this register, I don't have to go around looking for the register and its value and all that. All I do is write this value and I write, let's say, hex. That's all I have to do. I don't have to do anything else. Okay. So what are the other things that we have to do? First thing we have to do is we have to enable GPIO digital, right? So digital enable. So let's take a look and see if we can find the digital enable register. So DEN is what we are looking for, and that is this one. So let me see if I can put this side by side. Yeah. So now DEN is this. And what is the value that we want to write to this? We want to write digital enable, we want to write hex 1x. Okay, so let's write hex 1x. Okay, and let's go in order. So first you have to enable the digital outputs, which we have done. Next thing we want to do is this open drain. I don't care about. Pull down, pull up, we don't care about at the moment. Of course, pull ups you may want to enable. So let's go and enable the pull ups on the two input pins. So which are the two input pins? The input pin is here and it is here. So if I want these two to have pull-ups enabled, so 1 and 1 here, so that means the value that I have to write is 1 1 in hex. Okay, so this is my pull-up enable value. So let's go and write pull-up enable hex 1 1. So where is my pull-up enable? This is my pull-up enable. So digital enable pull-up enable register hex 1 1. Right? Pull down enable, of course I will enable pull ups, I don't need to enable pull down. Slew rate I don't care about. CCTL we don't need to use. Then GPIO DIR. So I need to consider these ports as outputs. So to do that, let's go to DIR. This is port F direction register. This is my DIR, and here I need to set only those 3 pins RGB as my output. So XE X0 E, that is my output. And the final thing I need to do is actually write to the data and that is this. Okay, and so if you don't want to do anything else, so I'm going to just put a while one here, and basically my processor will get stuck in this loop, and that's it. So let's see if this LED, which is where is our LED? Is somewhere here. Let's see if it lights up. So let's first do a build. You can see that my program basically has no idea about what this is, and that's because we have not done hash include. So let's include this file. So hash include. So there we go. And by the way, control space is a nice autocomplete feature. So if you type something and then press control and space together, it will try to autocomplete and guess what you are trying to do. So let's try and build again. Build project. Okay. So now we are getting a warning. Dynamic initialization is in unreachable code. So which is a valid warning because this particular code is never going to be reached. So just to keep this compiler happy, let me move this piece of code up here so that it will get initialized, but it will never get used. So that's okay. So let's build again. Again, one more warning, loop is not reachable. Okay, so this loop is not reachable. Again, we can ignore this particular warning because I know what I'm doing. So build project and let's debug. Okay, so let's see if we, there we go. So now let's start running things one by one. So first instruction, you can see we have reached here. Okay, so LDR, PC, and then some offset. So we have done this. We are now loading value XF into this register R0. Okay, so let's do this, and now this is going to get stored. Basically, this is going to get stored into this actual register. Okay, so let's see whether that actually happens. So the register that I'm interested in writing is called this GPIO port F DENR. So let's go and find this register here. So Control F, find items by description. Let's see. Okay, so maybe it will be digital enable. That will be port F. So the names of these ports are slightly different. So let's just check. So port F. So this is our port F. Clock waiting control, reset control. Okay, not. Maybe it's listed under GPIO. So GPIO DEN port F. This is the register that we are watching. Okay, so there we go. GPIO DEN. Memory return. Memory unable to read. Why was it unable to read? Let's just try and figure out what's going on here. GPIO port F. It was not able to read this particular one. Okay, let's continue anyway and see if we are able to get past this. Okay, so we are able to do there we are. So we are in fault ISR, which means we have made some mistakes somewhere and we have ended up inside this fault ISR. Okay, So now let's go and see why uh, this happened. Okay. So I will come back.